Okay, so we are going to look at a demonstration of how to simulate the ALU design along with the test bench in Xilinx ISE software. We're going to use the integrated simulator within Xilinx ISE. Later on, we are going to generate a timing diagram, analyze the timing diagram for functional verification of functionality of the design, and later on, we are going to synthesize and implement the design for a particular device. This is the screen that you see when you open Xilinx ISE Project Navigator. You create a new project. Let's call it ALU. The location should be where your VHDL files are saved. So I'm going to choose that. Working directory is the same. Top level source is HDL, hardware description language. Family is Spartan 3 3S400 device, PQ208 package. Synthesis tool is XST, simulator is ISIM, preferred language is VHDL. Click OK. I've created this project, so I'm going to add source to the project. Source is my VHDL source. So I'll select the main design and the test bench. Say open. The test bench association should be simulation only because we're going to simulate the test bench, whereas the design should be all. Say OK. If you go to simulation view and look at the design, I'll explain briefly how the design is done. These are the libraries. I will talk about briefly about this design, not VHDL in general. So the presumption is that you are already aware of VHDL as a design language. So there are libraries declared, entity is declared. Entity is where you declare the input output ports. Clock and reset are single bit input. A and B are single bit. A and B are 4-bit input ports, standard logic vector. These are the operands. Enable is used to enable the design, single bit input port. Opcode is 4-bit input port. This defines which function we are going to perform in the ALU. ALU out is the output port which is 8 bits and which carries the result outside the ALU design. Architecture is where you declare the logic of the design. We have process which is sensitive to clock signal. So any change in clock signal will trigger the process. If reset is 1, ALU out gets 0. Else if rising edge clock, so this is going to detect the rising edge or the positive going edge of the clock. Then you execute this case statement. When opcode is 0001, you're going to have a plus operation or the addition operation, arithmetic addition. Since ALU out is 8 bits, I am padding the MSB 4 bits with 0 with the result of this operation and will give you the concatenation. When opcode is 0010, we are performing a subtraction operation. When opcode is 0011, we are generating a A's complement. Whatever A value is complemented. When opcode is 0100, it's a multiplication or logical AND or logical OR or logical NAND or logical XOR. Finally, we end the case, end if statement, end process, and ALU architecture. Let's look at design test bench. This is called test_ALU.VHD. Similar to the design, there are libraries declared here. Test bench doesn't have any entity ports because test bench entity is always empty. Architecture of the test bench. We are declaring the component that we are going to instantiate. Then we are going to declare the local signals. We are going to instantiate our design, which is the ALU in this case, and map the local signals to the port values of the ALU. This is a process which is going to generate free running clock for you. Finally, we come to the process where we are going to apply the stimulus to the design. We apply reset for 1 clock cycle, then we assign reset 0. Then we apply the operands or the main inputs. A is 0010 means 2. B is 0001 means 1. Enable is 1, so my ALU can perform or function. 0001 means it's a arithmetic addition operation. Then I wait for 1 clock cycle. I keep the A and B values same. Then I say opcode is 0010. It's a subtraction operation. So on and so forth. This is my test bench. Finally, I end the process, end the architecture. Okay, so let's do a simulation or generate a timing diagram. So I go to this, I select simulation view, I select test bench, I expand ISIM simulator, I double click on simulate behavioral model. So it's going to generate a simulation timing diagram for me. Let's wait for a minute till it is generated. Okay, so I can click here, I can say zoom to full view where I can generate the complete view. So this is where all the action is happening. Let me zoom into this area a little bit. Let me try to analyze whether my design is working correctly or not. This is a free running clock. Looks good. I've applied a reset for one cycle, then I make reset 0. So I've resetted my design. At this point, positive edge of the clock, because all my design is working with respect to rising edge or positive edge of the clock. My enable is 1. At the same time, my A and B inputs are applied. A is 2, B is 1. If you right click on this and say radix binary, you can see it in binary values. Otherwise, by default, it is hexadecimal for me. So A is 2 and B is 1 and operand is 1, opcode is 1. Opcode 1 means I have to perform a arithmetic addition operation. 2 plus 1 is 3. My ALU out result is 3. Looks like design is working. Let's look at the second case. Next positive edge of the clock. A and B values remain the same, 2 and 1. Opcode has changed to 2, means I have to perform a subtraction operation, arithmetic subtraction. 2 minus 1 is 1. Output is 1. Seems to be working. Next operation. A I have changed to 1111. B I have changed to 0111. Opcode is changed to 3 here. 3 opcode means I have to perform a A's complement. 1111 complement means 000. If I change ALU out binary to this, it will be 000. Remember, ALU out is 8 bits, whereas A and B operands are 4 bits. So it is 8 bits, 8 zeros. So on and so forth. So since seems to be that my design is working as per the timing diagram. I close this timing diagram. Now my simulation is over. I want to synthesize and implement my design. For that I have to change the view to implementation. We only implement the main design, not the test bench. So I select this design. The first step is synthesize. I right click on this, say run. I'm going to synthesize my design. The synthesis process will convert my VHDL design to netlist. So let's wait till the synthesis part is over. Right side top corner, this is where you see the design summary. Implementation current is synthesis or synthesized design, no errors. Looks good. Next step is implement the design. Right click on implement the design, say run. So implement the design will internally translate the design, map it, place and route it. And will generate a timing report. So let's wait till this step is over. So implement design has completed successfully. If you see right hand top corner, implementation state, placed and routed, no errors. Next step is generate programming file. Right click on that and say run. Generate programming file step will generate a bit file for you, which you're going to download on the FPGA kit that you have. Generate programming file completed successfully. The same will be reflected in the design summary here on the right hand side top corner. So after generating the bit file, there are different ways to program your FPGA. You can do it through Xilinx, or depending on the kit that you have, the kit vendor will give you a separate software to program the FPGA using the bit file. So depending on which kit you have, you can program the FPGA with the bit file using the appropriate method. So this is where we conclude our demonstration, where we have seen the design creation, test bench creation, simulation, synthesis and implementation. This is the entire design FPGA design cycle. Okay, thank you.